Hi, hello. Thank you for attending this webinar. I'm Ronald Siat from CivilFEM development team. Along with me is Roman Martin. The two of us will present you some of the main highlights of this upcoming release of CivilFEM 2017. We will start talking about who we are in Cyber as a company developing CivilFEM software. We'll explain some of the things of what we do and what's CivilFEM, and you can ask any question using the chat tool anytime, so we can answer any of your questions online in real time. So we can start just now. So what's in Cyber? It's a company specialized civil and mechanical computer-aided engineering company with more than 30 years of experience supporting and distributing a finite element method-based solution, including consultancy, software development as CivilFEM. And after that, giving technical service and support. After all these years, we have a high expertise in structural, civil, and mechanical engineering, and as well as CFD projects. And we we share our knowledge, educating engineers and technicians all around the world, using our masters and our international education online center. Later we will show you the way of sharing this knowledge. We have supplied over 3,000 CEA program, including commercial, university, and educational licenses. CivilFEM is a software developed by Cyber. Many of you must already know CivilFEM because our first CivilFEM, which was developed, is the one using ANSYS as solver. But this new version since 2012, which has been improving and being polished until today's version, is the CivilFEM powered by Marc, using the powerful nonlinear Marc solver. This new CivilFEM, since as I told you 2012, will give you a unique and best solution for your civil engineering needs. CivilFEM will cover all your analysis, including geotechnical, dynamic, bridges, processing concrete, and now we will present these new capabilities for this new release, including heat transfer and prestressed concrete as main improvements, besides other interesting tools which will be shown to you in the following slides. One of the main improvements of this 2017 version is the definition of tendons, of prestressed tendons in all type of available all elements, actually beam, shell, and solid elements. Using the complete list of tools in the geometry tab in CivilFEM, we can define the path of each of our tendons, and automatically the losses will be calculated. All losses, immediate losses due to heating, to thermal steel expansion, frictions, slippage of strands, elastic shortening, and as well the long-term losses, the concrete shrinkage, creep, steel relaxation. Okay, later prestress check according to the all available prestressing codes and standards. Later we will sorry, go back. We will we can plot the isostatic and hyperstatic forces and moments, and of course we can plot the interaction diagram of these sections, both passive and active reinforcement can be taken into account always. We can show you this in an example. So this we have this model. It's a solid model. We will show you a solid model using solid elements and a beam model. We have the definition of our volumes. We have defined this 3-span slab bridge. Okay. Well, its span length it's about 30 meters, and we have defined solid diaphragms between one slab and the following one. These ones, this solid one, and we can see that we have defined this voided slab section, and between them we have defined some solid diaphragms. Okay, we can see as well the tendons. We can define our tendons using any of these available cubes, spline, with curves, arcs, any tool, or we can use external file if you want to work with another software and import your geometry. You can always use it. And this is the bridge, and the tendons are defined using a parabolic path in plan view and in elevation view. We can have a look. Here you have our bridge, and the tendons are here defined. You can see that the tendons are defined here using this path, and for the last last span we have defined as well a parabolic path in plan view, as you can see here. You can see here. This is just the geometry following a parabolic shape. These first two slabs are almost straight, and this last one is curved. So we have defined a parabolic shape in plan view and in elevation view. Okay. So what's the next part after the definition of our geometry? Then we can mesh. If we mesh using our typical tools, and first of all we have to define our cross sections. In this case we have defined the section of our tendons. We have two types of tendons of the two different diameters, and if we mesh, here we have our mesh. We have our solid elements using the extrusion control, which is very easy to mesh. Then we can apply our prestressing loads. Here you have the different options: prestressing on beams, shell, on solid. In this case we have defined prestressing in solids. We can see here the definition of our tendons. Here you have them. The tendons here for the first span. These are the tendons for the second span, and we have defined tendons for the second span. Sorry, third span. And these are the solid structural elements connecting the different voided slab spans. So what's in how to define our prestressing tendons? We just need to select a path, our prestressing technique. It can be post-tension or pre-tension. The prestressing can be defined by forces, and then we can add our different tendons. In this case, we have defined three tendons. Excuse me, 4 tendons for each span. You can see them here. 4 tendons, and each one has different diameter. These are 70 millimeters, and these are 100 millimeters. Okay, here you have them. And then we can add the tendons, and we can set the diameter of the casing, the prestressing stress. In case we are going to use evolutive or construction stage analysis, we can set the activation and the activation age. We can set the order of prestressing, the creep stress, and one important thing is that the losses are automatically calculated. Here you have them, depending on the code and the code properties of the material. And of course, we can show here the path of these 4 tendons of last span. This is in plan view, and this is in elevation view, and it's very easy and very powerful, this last improvement. So if I turn on all the structural elements, here we have them. We have defined boundary condition, just these boundary conditions. We just set constrained all degrees of freedom at the end and the beginning at the end of the bridge, and just simply supported in the middle supports. What other loads we defined? The other loads is just gravity and traffic load on the bridge. So we just need to solve. Here we have our load cases. We can define different load cases, including only self-weight, self-weight plus traffic, only pre-stress, and the last one is the we can first show you self-weight plus traffic, for example, and we can see results. For example, we can see you can see here displacement. The maximum displacement is here on this part. We can turn on the clipping option. It's very useful. Here we have them. And we can see, as we have solid elements, we can always see results in the internal elements. In this case, we are just plotting displacement. Of course, we have our we have stresses and strains, any type of available results for these elements. These are the results for the lab case without prestressing. Have you seen the results? Now if we select the one with prestressing, we can now check the difference in results. In this case, we will plot again results. In this case, now we have a deflection, a maximum deflection of 22 millimeters, because it has been taken into account the prestressing tendons, which are these ones. Okay, you can check us again results. Here are the maximum deflection is on this part, which is the in the curve. It's obvious, which is located in the curve part of the slab. So if we want to perform code checking using any of the available standards and plot the interaction diagram, we can simplify the model and use a beam model. So we open the other model. It's using beam elements. In this case, we have to define cross sections. Two cross sections, a solid section and a voided section. We can always plot insert passive reinforcement. In this case, we have defined only the tendons. In this case, you can see that these are just beam elements using linear elements. This will take less resources, and we use less number of elements, and of course later we can plot the available new results, the isostatic and hyperstatic forces and moments, and plot the interaction diagram of any cross section, any element, any beam element. These are the available codes for prestressing. In the material, we have our code properties. And of course the same for the section. And we just need to define our geometry, just lines. You see them. And once we mesh, we just apply, we just use our typical mesh controls for beams, which is in this case a uniform number of elements for each structural element. And then the same, to define our prestressing, we just need to set forces. They are set in this case on beams, and the loads are the same. You can see here. Here are the tendons inside the elements for each span. Maybe it's better to hide them. For the 3 spans, and then we have defined the traffic loads. Okay, here we have it, and we have defined traffic loads, and the results are the same. We just need to select our last result, and in this case we can plot nodal results. In this case we want to see forces and moments. In this case, we can plot it in in 2D. Maybe it's better to you can plot the total moments. But as I told you, we have available now the isostatic and hyperstatic forces and moments. This is not the right axis. Z is the predominant axis. Bending moments, transverse shear. You can see here. Okay. Always you can use any kind of units to plot our forces and moments. And of course we can perform a code checking. We can check prestressing elements in this case, and our typical results are the total criterion. Is the total criterion, which will give us, well, if the sections are safe or not safe. If I take out the results of the first fixed element, which taking all the stresses, we can see all these sections. If we want to plot, for example, the result, the interaction diagram of a prestressing beam, this beam, we can see the result. Okay, as you can see, well, the ultimate strength is this value, and the external actions are below the ultimate strength. So the criterion is states that the cross section is okay. This is the area of the prestressing steel yielding, this green part. The pivot of the concrete are the blue and red. So the section is considered safe because it's below 1. If you always need help for anything, here we have the help for the tendon and prestressing, or the formulation, taking into account for each code. It's well documented here in the online manual. So we now explain the next improvement. The next important highlight, the next important improvement is the heat transfer. So the capability to for 1, 2, 3 dimensional steady state or transient analysis. This new capability allows you to obtain temperature distributions in a structure for linear and nonlinear heat transfer problems. So in this case, new terms will be taken into account with some difference with the structural analysis. The displacements, forces, and pressures will be in this case defined as boundary conditions, terms of temperature, heat flux, thermal flux. New properties are taken into account: thermal conductivity, specific heat, emissivity, constant field coefficient can be taken into account. You can see that the heat conduction and convection are new here in the heat transfer. And you must take into account that the thermal conductivity can be isotropic or orthotropic. The thing is that the CivilFEM provides heat transfer elements that are compatible with structural elements. So the same mesh can be used for both heat transfer and structural analysis. We will see that we can use a couple analysis. First, solve thermal analysis, and then take the results for a structural analysis. That's very important, very interesting. So later we can plot our typical structural results, displacement, stresses, and then we can perform a code checking and plot forces and moments. In this case, proper initial and boundary conditions must be prescribed to the problem in order to obtain a realistic solution. One of the typical results for thermal analysis are temperatures. We will see this in a simple example. So we go to the example. This is the example. Well, if we want to open a new analysis, a new thermal analysis, we go always to here, thermal structural analysis. If we want to perform a couple analysis, always as well click on thermal type of analysis. This is the one. This beam prestressed. This is a prestressed beam. Here we have defined a prestressed beam using the tools that we have already explained in the previous slide about the tendon definition. And what we are gonna do is to perform a couple analysis. First, we will see how to perform a thermal analysis. In this case, we applied here, as now it's a boundary condition. We have, once we open a new thermal analysis, we have new icons, new buttons for a thermal boundary condition group and a thermal load case. We have defined a thermal flux on the full beam of 30 watts per cubic meter in the full beam, and a boundary condition, a temperature. One of the available options for the simple boundary conditions is a temperature in a surface, and the temperatures will be applied at the bottom of the beam, and we will see how the temperature will be be distributed all along our beam. The temperature is 100 Celsius degrees. Okay, we can use always any kind of units, and we have select this bottom surface. Okay, so what we're going to do is compare first the results of a thermal or only thermal analysis, then use a structural couple analysis and see the displacements on a structural analysis after importing all the results from the thermal analysis. Then see the effects of only the prestressing, and then see the coupling of the prestressing and the thermal and the couple prestressing, and a couple analysis of thermal and prestressing. We'll see the different results. Here we have them: thermal, structural prestress, couple only temperature, and couple prestress. We can always define mix different type of analysis in a couple analysis. So what we're going to do is to open only the thermal case, and we can see here the temperature. We have applied 100 Celsius degrees the bottom, and we can see here how is the temperature distribution after having, well, of course, important thing is always to set the heat transfer properties. Okay, the thermal conductivity definition, we can set always a orthotropic condition, but in this case we have defined, and important, we can define always a non-linear definition of conductivity. In this case we have defined a non-linear conductivity. Okay, this one from 0 to 30, a value of 1, and from 30 it will take a value of 2 watts per meter by Kelvin degree for the concrete material. That's very important. That's one thing that it's new in the material definition. If we are using a heat transfer or a heat transfer and a structural coupled analysis. If we open then the coupling analysis with only temperature, then we can see results of the structural analysis. So taking with the same mesh and same elements, you don't need to do anything else. We can see here the deflection of our beam due to the temperature definition, or the flux of the temperature applied on the bottom surface, and take into account the constant flux on the full beam. If we open only a structural prestress, we can see now the displacement, instead of the deflection going going negative deflection. In this case, due to the effect of the prestressing tendon, we have a positive deflection of 10 centimeters. And now, if we want to couple the prestress plus the thermal, okay, this is only the, in this case we just plot only the structural prestressing. We will see the combination of the two of them. Now you will see this all completely without any deflection. Well, just some millimeters, but it has combined the deflection, the negative deflection due to the temperature, plus the positive deflection due to the prestressing, and the final coupling of the two of them is this result. Okay, this is very interesting. Very the coupling of two different analysis types. So we continue. Another important improvement is the analysis restart. Very important, because it will save us time and resources. If we have many multi-load case analysis, we can start always from a previous one solved, so we don't need to start from the beginning. So if we have our software, in the solve tab, we can create a restart file, or we can read it. here in this group from this tab. Okay, so if we continue, we have new improvements for the material models.
For the material models, we have done many improvements. One of them is improving the convergence of the material models, especially Cam-Clay and Mohr-Coulomb. So now we are able to converge much more difficult situations, stress configurations. And well, also for Cam-Clay material model and Mohr-Coulomb, we have also improved some of the capacities. For Mohr-Coulomb, we have introduced variable cohesion and friction angle. We can introduce those values as a constant value or also using a table. If we just check in the software, the steps are just in the model, just selecting a soil, any of them, and after selecting it, we modify the behavior and set to Mohr-Coulomb. When we have the Mohr-Coulomb, here in the values of Mohr-Coulomb, we can add a constant cohesion, for example, 10 kilopascals, and the same for the friction angle, or we can click this button and set in a table variable values. Just we can add here different rows. I'm going to delete this one and add difference. And well, this is the strain, the plastic strain, tangent plastic strain, and this is the value for cohesion. We can set with different points any sort of curve. It could be, for example, increasing this value. We can add another row here with a constant value here in example, and insert other. So we can add any sort of configuration for cohesion that could be a variable with a residual value and a variable value that depends on the plastic tangent strain. And the same for the friction angle. In the friction angle, we can also modify and set it by a table in the same way. Okay, so when adding these variable values, just when solving, just these values are modified considering the yielding stress, the yielding strain in the material. And the other options are that we have improved are for a Cam-Clay model. For Cam-Clay model, we have added different variables here just to improve its behavior for much more accurate value. Those values are these ones. Well, these are the typical Cam-Clay values. I'm going to show them in the PPT file. And well, here we can see that the typical values of the Cam-Clay model are the isotropic compression line, the unloading reloading line, that are these slopes, and these slopes depends on the over-consolidation state. If we have an over-consolidation state, first the loading line will follow this slope until we reach the prestressed reconsolidation stress, and then from this point we continue by this other slope, and yielding starts. Well, the points that define this over-consolidation stress are defined by this type of ellipse. This ellipse is defined by E, that is the radio of that, and also there are some coefficients, beta and pt, that displace this curve towards left to add tension stress on the model, and also this other beta value just to reduce the curve in this zone. So we can define different shapes for this ellipse and to define the over-consolidation stress. If we solve a model like this with solid models where we apply a triaxial stress on top until this model is broken. If we add overconsolidation ratio equal to 1, we will have this curve. Adding overconsolidation of 2, first we have elastic behavior until we reach this point. We leave this ellipse, and then we have J-line with this other parabolic. And if we have overconsolidation of 5, the stress line will follow this zone until reaching the ellipse, and then will fall the stress until this curve, this line. So we'll have these results for overconsolidation, for high overconsolidation clays. If we open the model, we can see the results in the history plot, selecting results, plotting results in one of the elements, in example this one, 85. And if we plot in example for this case that is overconsolidated, we plot vertical stresses, we can see we have this type of curve. If we just open another example in this model, we can see that the overconsolidating ratio is equal to 1. If we select the same model but with overconsolidation equal to 2, and we plot strains, we can see now we have this behavior, first elastic behavior and then a curve until completing J-line and collapse of the model. And the final result for the high overconsolidated clay, we will have this other behavior we can see in this curve. So we can see we have much more parameters for a much more accurately material model with Cam-Clay.
Well, other improvements are these ones: conical projection for 3D view, video animation of results, very powerful, and numerical results on finite elements. And now we can just pick an element and the result will be shown in the graphical user interface, and improved generation of reports. All these will give us a better post-processing. We can see here, for example, some of these improvements. The conical view. If we want to result, we just go through the elements, as you can see here. In previous versions, this wasn't available, and as well, here you can see the conical projection, more impressive. Okay, and we have as well another option, which are the video animations. Here we have this button. We just select our results, our result type, and we can animate. In this case, this is a bridge. We can animate our model shapes just by selecting our results. We have them available here, and of course we can save them and generate images files if you want to add them to in a batch mode, so we can have all our images saved, so we can add them to a report. So this is very interesting. And last but not least, please, this important information, please visit our website, CivilFEM.com, and International Computer Aided Engineering and Education Center. Here you have the websites, these ones. And well, this summer, InkeCyber celebrates its 30 years dedicated to the finite element method, an added value to provide the best customized technical support, training, and consultancy services, offering always integral solutions for your projects. Therefore, for this 30th anniversary and the launching of this CivilFEM 2017, we have prepared a special promotion with important discounts until September the 30th. Please contact any of these emails, info contact, or depending on the area, you have Cristina Rodriguez or Eduardo Garcia, to know all about these special promotions. So thank you very much for your attention, and as well a short survey will appear at the end of the session. Please just take a couple of minutes to complete it. Thank you. See you in the next webinar. Thank you. Bye.